Ladies and gentlemen, a very warm welcome to you all. Today, as you know, we are gathered here under the auspices of DEİK to shed some light on certain aspects of nanotechnology. In this respect, we have here well-known academics, managing directors from both the Czech Republic as well as the Republic of Turkey. The subject before us is, as you know, DEİK EU talks, new developments in nanotechnology and its effects in the near future. The session will be moderated by Mr. Öztürk, who is also a board member, like myself, at DEİK Czechia Turkey Business Council. And the distinguished contributors we have here will be Professor Kush, Professor Demir, Professor Slovoda, Mr. S. from Kalyon, Professor Lucas, and Jan, and I hope he arrives here soon. I wish to thank you all for your presence and give the floor to Mr. Öztürk, please.
Thank you, Mr. Ekman. Welcome, everyone. Thank you for joining us today webinar about nanotechnology. My name is Berkan Öztürk and I am moderating the webinar today, and I am excited to be hosting this session. Dear participants, if you want to listen this speech in Turkish, please click the Japanese option in the interpretation section at the bottom right of the screen. If you want to continue in English, please choose English. I am General Manager at Nanomats. Nanomats is a provider of nanotechnology in Turkey. My background is studied material engineering, 9 Eylül. Also, I completed my master's degree in nanopowder production. I'd like to welcome you on behalf of DEİK. By the way, thanks for magnificent settings to DEİK. Today, we are presenting new developments in nanotechnology and its effect in the near future. I know that today's two topics may bring up a few questions from you, and I want to let you know that I will address as many as I can in the time today. If you have any questions during the presentation, please type them into your question box in your Zoom control panel. I will bring them during the presentation, and we will have also time questions at the end. As you know, nanotechnology is a rapidly growing field that touches pretty much every STM area. In a new world, where technology is evolving at a pace much higher than any point of the time recorded history, nanoengineering is pushing the boundaries of conventional technologies practice. It is helping engineers and researchers all over the world not only improve the current line of products and technologies, but to develop entirely novel functionalities achieved by the bottom-up approach of the construction. I would like to give some information about also Czechia. Czechia, which is one of the countries that invest the most nanotechnology in Europe, is thought to have many important inventions and products in the near future. I am pleased to introduce today's speakers, Jiří Kus. Jiří Kus, a Czech businessman, chairman of the Association Nanotechnology Industry of the Czech Republic, promoter of nanotechnologies and the concept of the third industrial revolution of the American economist Jeremy Rifkin. He studied industrial energy, later also sociology. He has been involved in industrial automation, foreign trade, and marketing for 20 years. Since 2014, he has been actively promoting lectures, interviews for the media and public appearances to promote the concept of the third industrial revolution. So without any further ado, I would like to kick things off by welcoming Czech Association of Nanotechnology Industry Chairman, Jiří Kus. Mr. Kus, over to you.
So thank you for the nice introduction. Today I would like to speak about Czech nanotechnology in the connection with the pandemic situation, and to give you some overview, some scope of what we what we did this year and how we are helping to keep with pandemic, which is a very difficult and bad thing for all countries. And in fact, it is also example how the advanced material technologies can help people in healthcare. Okay, so can I start a presentation?
Please.
So as you mentioned, Czech Republic is quite strong in industrial application in nanotechnologies, and we say that we are one of the nano pioneers in industrial application, because Czech Republic has from one side very strong engineering tradition going back to 19th century, and also high level of education in chemistry, physics, and biology. And it makes together very good and strong base for nanotechnology development. You can see on that picture many trademarks, which are the companies that have nanotechnology as their core business. So we are not on the stage of prototypes, we are on the stage of industrial production of different nanotech products. And you know that nanotechnology is crossing all industrial branches, from biotech up to textile and batteries and optics and things like this. We are specialists in different things, but especially in nanofiber. Today we have together two scientists from the university in Liberec, where in 2005 the patent for industrial production of a nanofiber was done. And nanofiber is produced like a very tiny nanomembrane with very small tiny fibers and small holes, small pores, which is very good for the filtration. And once you are in a nano world, on a nano scale, you can filter, you can stop very small particles like dust, small droplets, allergen, bacteria, and also viruses. And it is the key point that we can use nanomembrane for the protection against viruses and also against coronavirus. You can see that when you measure the filtration under 1 micron, a nanofiber is very successful, and certain types of nanomembranes can reach the level of the filtration like 94% of the viruses with the size of coronavirus. So it is very interesting solution. In fact, in the world, we are not the only one who decided to use nanomembrane for the filtration of viruses and bacteria, but we are let's say one of the niches in the world for that technology. But anyway, how was the situation at the beginning of this year when we heard about pandemic, that it's happening in China, and in January we were scared it's coming to also to the other countries, to Europe and Middle East and so on. It happened. So in Czech Republic we had in fact two industrial manufacturers of nanomembrane. It was the company Nanotech, former Nanovia, and the company Pardam, with some quantity, and we have very small production of nanofiber respirators, but the quantity like 10,000 pieces per month, so it was almost nothing. When pandemic came to the Czech Republic, it was very bad, very difficult, and there was not enough face masks and respirators in our country. So the government started import from China and so on. But at the same time, nanotech companies started to mobilize their production and invest millions of euros to increase the production, buying new machines, and also many companies starting to produce face masks made with nanomembranes appeared. And in summer 2020, we had, instead of only 2 manufacturers, 5 manufacturers of nanomembrane. So it means totally two new companies, 2 new factories. And we had also a quantity of manufacturers of nanofiber face mask and 2 manufacturers of nanofiber respirators. So at that moment, the production of nanofiber face mask in Czech Republic is something like 10-11 million pieces per month. And it can still go up. There's possibility to even increase the production. And regarding nanofiber respirators, we have two manufacturers, the company Paradigm and the company Spur. And the total quantity per month is something like 4.8 million nanofiber respirators. So you can see the strong mobilization of the nanofiber production, what happened in the Czech Republic. And that moment we say we are, in terms of nanofiber or face mask and respirators production, independent. So which is amazing. And at the same time, when we talk about nanofiber face mask, it is a kind of new product which is very close to respirators, that it's catching viruses not only from your mouth, but it is also protecting you against the infection which is coming from outside, from other people. So what is also very interesting, that the investment the companies did was made from private finance sources. So it was not depending on the state or state funds. It was from, I don't know, 99 or 95% made from private money. So you see that at the moment we have really large portfolio of products, even nanofiber antivirus cards using the shield from nanomembrane, which is in that product, again, protecting you from coronavirus, and different kinds of face mask, also child face mask and respirators. So from my side, that's all, and I hope I gave you the good example, or real example, how nanotechnology can really help people to protect their health. And because when I'm thinking about pandemic, about those time, I believe that after pandemic, the world will be changed, and probably also the level of the protection of our health, of the protection against infection, will be much higher. And I believe that nanotechnology and nanofibers can play a very important role in that new world after pandemic. Okay, so that's all from my side. I don't know if we will continue and we want to give some question.
Thank you. Thank you very much, Mr. Kuz. If you wish, let's continue with the questions at the presentation of all speakers at the end.
Okay.
And I also heard some highly successful business stories between the two countries recently established by the entrepreneur who was part of the nanotechnology research group at the Istanbul Technic University in 2005. Artekia firm was established in Czechia in 2018 to manage European operations with the help of DEİK agency. And we hope that we'll increase the same stories in the near future. Now I want to give some information about the Turkey and Bilkent University Research Center UNAM. Turkey, the European Union actively participates in the research and innovation program, which since Horizon 2020 in 2014. As the first of 6 months of 2019, more than 700 public and private companies and universities have earned 266 million euros in more than 500 projects, with a total portfolio of 2.3 billion euros financed under the Horizon program. Like other research institutions in our country, Bilkent University also applies the Horizon 2020 program and other programs for research support. And many projects are currently supported by both our country and the European Union projects. As a metric of quality, according to Nature Index journal publications, Bilkent UNAM ranks #1 as a research institute in the country, accumulatively contributing to approximately 7.2 of Turkey's entire Nature Index journal publications to date. Now I would like to give some information about our next speakers. Hilmi Volkan Demir started his undergraduate educations with a full scholarships in the Department of Electrical and Electronics Engineering at Bilkent University in Ankara. He received his master's and PhD degrees in electrical engineering from Stanford. Dr. Demir is a currently full professor of electrical and electronics engineering, of physics, and of material science and nanotechnology at the Bilkent University. He also been appointed as the director of the National Nanotechnology Research Center of Turkey and served as the director of the Institute Material Science and Nanotechnology and the head of the Material Science and Nanotechnology graduate program. As a PI, he has successfully completed over 60 national and international projects. He has been selected to the Science Award in 2020. So now I would like to welcome Bilkent University Director of National Nanotechnology Research Center, Hilmi Volkan Demir. Professor Demir, over to you.
Well, thank you very much, Mr. Chairman, Mr. Berkan Öztürk. It's my great pleasure to be here today. Thank you very much, the entire community, for your kind invitation. It's absolutely great pleasure to also have colleagues from Czech Republic. I had actually good friends over the years I developed in European programs, and I worked really well closely myself, but also as an institute with a variety of scientists. So it's also, therefore, my great pleasure to be here today. Given the time I have, I'd like to share with you our journey in nanoscience and nanotechnology. And for that reason, I'll be showing you a series of slides. This will be a short presentation. And I suppose you can see now my screen. May I please verify that you can see my screen? Can you see my screen?
Yes.
Yes.
Yes.
All right. Thank you very much. So I will take you through a different direction. And in this case, I'd like to talk about an emerging material system and its new applications. And this is the so-called semiconductor nanocrystals. And I'll be focusing mostly on their optoelectronics. And this is really a journey for us, starting from colloidal quantum dots. These are three-dimensionally confined structures. You can call them quasi-zero-dimensional, to wells. When we say wells, we are really talking about atomically flat nanocrystals. And you will see the effect is happening. This is happening as we speak, but I will extend to the near future as well. Once again, I'm Hilmi Volkan Demir. I go actually by my middle name, Volkan. And maybe you do know, this really means volcano in Turkish. It is a very funny story, in my opinion. because Hilmi, coming from my grandfather, is a very old Turkish. It has roots from Arabic language, and it means naive. It means pure. But my last name, which I think will surprise you, means really the element iron. When you put all these together, I become the pure volcano iron. And it's funny that my parents didn't know I'll be working many years later on materials. And this is what I like doing. So I work at Bilkent University, UNAM. UNAM stands for the National Nanotechnology Research Center. At the same time, at Bilkent, over 10 years now, we have MOU, Memorandum of Understanding, with NTU Singapore. For that reason, we have the operation, both NTU and Bilkent. And what I'll be presenting is indeed the result of this joint effort. As Mr. Chairman explained, UNAM is a national lab, and as a national lab, it is a research hub, and it is indeed a center for talent attraction within the country, but also in the region. The way we see this, we are really is an opening window, and we work very closely with the entire world, including Europe. With European Union, we have a lot of close partners, and we surely would like to have more interaction and collaboration with Czechia. UNAM by numbers, you can see here variety of metrics. Maybe I'll highlight a few. We had 23 high-tech startups spun off UNAM. And indeed, if we check out the contribution of these high-tech companies from UNAM, the contribution is in the range of high tens to hundreds of millions of dollars, considering the high-tech technology developed. And being located in Ankara, we see more of these companies scattered in Ankara and in the region, but we do also extend towards Istanbul and Gebze region, where we have really quite successful startups. And some of these actually have became now rather large companies, where we do have professional business groups involved, and they were able to attract investments also from Europe. And that is maybe for me a takeaway message if there are those around in the audience interested in investment. Indeed, company is successful, and we are actively looking for new investments, and we do receive investment from Europe. We do also work with corporates. We do have a program which I think might be interesting for you. We call this Corporate Lab at UNAM. We can actually host corporates within UNAM, providing exactly the same research environment we do have here, which is cutting edge, to the companies. And this is not really a rental program. We really provide the entire infrastructure along with our expertise, the expert teams, including the entire know-how. Therefore, we work very closely with these companies, and we have been contributing to commercialization of high-tech products. You can see here we are scientifically quite active. Mr. Öztürk explained in great detail. We have a major visibility in the country and in the region, and we really try to work hard towards this excellence in science and technology. And maybe just to wrap up what UNAM is about, I'd like to use here a recent article that came out in Nature Nanotechnology, and this is maybe a better way to explain what UNAM serves for and what UNAM strives for. And this is by Professor Chris Çömi, writing about Bilkent University and UNAM. And this is in his words, Bilkent University in Ankara, Turkey, is an elite institution that focuses primarily on STEM, topics that is science, technology, engineering, math. And one of its crown jewels is UNAM. In Turkish, this is the National Nanotechnology Research Center. So we do have a national mission, and obviously this is a difficult task to carry. There's a big responsibility. And for that reason, we bring together a large group of researchers in the range of 400 to 500 to work towards this goal. Today, what I'll be presenting is mostly about my research work in my group, and for that reason, I'm very pleased to acknowledge the contribution of my team here at Bilkent, currently working, as well as those past members that have successfully graduated. And as you can see, they're now scattered all around the world. And some of them actually came back and became faculty members themselves. But you can see most of them have been to either Europe or US, including Cambridge, ETH, or in the US, Harvard, MIT, Stanford, Caltech, so on. And this is the group I am looking after at Singapore. This is a center, actually a sister center called Luminous. This is a center of excellence for semiconductor lighting and displays. And I'm working very closely with a number of my colleagues and the scientists and research fellows that work closely with me, as well as PhD students I train there. And this is our research program. We work very actively on semiconductor nanocrystals, and this is what I will be summarizing today. But not only nanocrystals, we look at their applications, particularly for lighting purposes. This is lighting and displays. We make actual light engines. I will just show a few slides in the interest of time. And I won't have time at all to talk about the work we carry on in implantable electronics, but I'd just like to say this is the entire research program we envision and running for 2 decades now. This is from Singapore. This work actually was initiated at Peking University, and with this MOU and investment from Singapore, we actually had our own epi wafer growth facility where we started from ground zero. We built everything, and then we developed these new generations of devices. You can see here, starting from lateral chip to flip chip to vertical, reverse vertical, different generation of devices that have been developed by us, and all the IPs belong to us. As a result, together with Singapore, we have successfully commercialized this. And indeed, now there's a company co-owned by NTU and ourselves, where we function both in Singapore and with our companies that we own in China. So this has been a success story, both in terms of scientific development and high-end technological commercialization. But what I'll show you is actually a paradigm shift. This is really happening because of the nanoscience and nanotechnology. And this has to do with a very old historical science known as color science. Color science is very well known and it is nothing new. But what is new is the way you generate your colors. The old common myth is that you generate the best color, for example, white, if you have broad emitters. So broad emitter, you can see one example here, which is well known, the so-called family of phosphors. This is really an alloy where you dope rare earth elements, and those are the emission centers. This is very nice, high efficiency, but the difficulty is to really control the emission characteristics. And it's very difficult to tune this emission like so. So our hypothesis was that instead of using this type of conventional continuous broad emitters, we can use a discrete set of discontinuous and sharp emitters. These are quantum emitters. And if you have the right strategy, if you have the right carefully tuned combination, actually you can do much better. And this was the new. At the time, this was not well received in old days, maybe 5 years ago to 10 years ago, but now this is well acknowledged, and actually it has been also used in commercial products. So this hypothesis was correct, and this was one of our demonstrations where we were able to show that using this type of sharp emitters, one can have extremely high color rendering property. This means you can really reflect the true colors of an illuminated object. You can make it warm white, and you can make it spectrally very efficiency. So these numbers at the time were highlighted in Nature Photonics. The difficulty was to reach these photometric metrics all at the same time. And this is indeed outperforming conventional phosphors. And phosphors also suffers one other problem, and that is the use of rare earth elements. which are more difficult to find, and they're available in only certain places. And as a result, they create a cost issue, whereas semiconductor quantum dots indeed can be made abundantly. And this is what we have been working, and several commercialization projects came out of it. I'll show you a few of them. One big program that is now running is with Vestel, and you might know Vestel. This is a Turkish origin country with headquarters close to Izmir, and Istanbul is a big group. But what is important in Europe, you may know Vestel because it is one of the top sellers in Europe in terms of screens. And indeed, you might even own some of their products under some other brands that they actually own and indeed manage. This type of quantum emitters are interesting because you can really make them at commercial level. This is one such example that was first shown at the time in a very large area, freestanding sheets. You can think of this as a freestanding or standalone membrane where you can make it several tens of centimeters. Here you see by 50 centimeter by 50 centimeter. And you can imagine the challenge here. We have these nanocrystals that you need to make quite uniformly distributed laterally over a meter scale, whereas you'd like to think about the thickness and also vertically have a reasonable distribution. And this technology was developed. Here you can see monocolor quantum dot film. We can even do bicolor. This is bifilm shown in flexed form. Of course, you can extend this type of color converters because they have this sharp emission, and you can use the right combination you want. If you illuminate them with some optical pump, collectively the color spectrum you generate can give you the best quality white light. This is very meaningful in artificial lighting indoors. You can do it for outdoors, specifically tuned. Again, this is possible because we have sharp emitters, but if you wish, you can use this also for example, liquid crystal display backlighting. And this is a project indeed directly funded by Samsung, where we had two projects in a row. And this was not only for color conversion purposes to have enrichment of the color span you can create on a TV screen, but also at the same time to have polarization control. So normally in a liquid crystal device, you need polarized light illumination, but typically you would start, for example, using LEDs or in old days fluorescent lamps, unpolarized light. So you immediately waste at least half of the photons. Here, the idea is to do the color conversion while you generate the right polarization you want and suppress the one you don't desire. And that's what we showed together with Samsung that created two patents co-owned by Samsung. And here you can see, in addition to the color conversion with spatial features, these are all nano features, we can actually suppress one polarization and induce only the one of our choice. Of course, for us, the question is what is next? And this is really important as scientists like myself, what is coming? We think both in lighting, especially high-end lighting, but also in certain cases, display-like applications, laser-based lighting will be critical. And there is a very strong argument for this, simply coming from efficiency issues. As we know well, LEDs with increased power density will suffer from thermal droop, efficiency droop. There is also a fundamental problem, the so-called ÖC droop. On the other hand, laser diodes can show increased performance. And for that reason, just to have significantly enhanced luminous efficiency, a lasing-based color conversion makes perfect sense. At the same time, you buy another critical advantage, and that is a better photon management ability using laser light. Of course, the simple question that will be posed is whether this is okay to do so. And the answer indeed comes from my good friend and close colleague from National Lab in the US, Jeff Tussauds, showing indeed laser lighting is indistinguishable by human eye if it is done properly. And here they compared with incandescent lamp and neutral white, cool white, and warm white LEDs. With that motivation, we have been developing these very spatial colloidal quantum dot emitters, and we can have near unity efficiency very, very routinely, and we can make devices very compact using what we coin all colloidal lasers. This is basically the quantum dot material is solution processed as well as the sandwiching mirror. So everything is very low cost and in principle can be applied quite large areas and essentially on any surface you desire. With that, we were able to show at the time record-breaking performance of these colloidal dots to lace from all solution-based processing. Of course, with that, we can achieve only a certain level of performance, and for us to push the limits is critical. And to push the limits, the answer comes from atomically flat family of nanocrystals, which we call nanoplatelets. The work indeed is inspired from French group in Paris. And what they showed is we can make this very well controlled atomically flat nanocrystals, either just core structure, or we can do shell, or just literally extend them to make core crown. And that's what we have been looking. This is what you see we can do in the lab, either putting face down or edge up. This is a paradigm shift because this indeed creates extremely large surfaces for us to work with while we keep the vertical quantum confinement tight. And this in turn means we have a really record level performance, which I will elaborate slightly more in the coming slides. With that idea, we demonstrated again this all solution processed lasers. And this was the highest performance ever reported at the time. We broke this record levels later in our group. We can do single photon, or as shown here, 2 photon pumped lasing. And this is more recent work. We have been trying to push the performance. And this is the highest net model gain, so the gain capability of these materials. To put this for you to a perspective, you can see the best results reported ever in the literature in their class: organic dyes, polymers, colloidal quantum dots. This is what we have worked ourselves as well. Rare earth doped fibers, epitaxial quantum dots is more conventional. They all reside here at room temperature. And these are the level of gain one can induce using this type of atomically flat nanocrystals. These are all at room temperature, but again, to put a big picture, I should also show you bulk gallium nitride at cryogenic temperature, 2 Kelvin, really cold, and bulk perovskite. So you see this has really, really competitive results. Once again, if you'd like to compare this with bulk semiconductor material, epitaxial quantum dots, organic dyes, organic semiconductor, colloidal quantum dots, now not model gain, but material gain, this is where our results fall into. Therefore, we are extremely exciting ourselves and with our partners worldwide, also a variety of companies we're working together. We think finally, this type of nanomaterials, extremely well engineered and high quality materials, will indeed challenge epitaxial conventional materials. We can use them continuously for long hours with some spatial designs as shown here. You hear now a 3-dimensional structure. We start with core, first do the crown, periphery passivated, and then shell coating everywhere. We can push these results. These are really quite recent, disseminated in Nature Communications, showing that you can engineer even better. And in this case, you can go extremely low level, unprecedented level of excitation to observe gain. This is per particle on the average less than 1 single exciton, meaning 1 electron hole pair. And this is, of course, being a physicist and electrical engineer, this is really exciting. We can push these results to show long hours of operation and lasing performance. This brings me towards the end of my presentation here. Just to give you highlight for near future, we can ensemble them all face down, all edge up, as shown here, really large scale. This will be, if needed, we can repeat them. This is almost a holy grail for us in nanoscience nanotechnology, because this is bottom-up building. We start with single particle, which we synthesize very low cost, large batches in solution, and then we can build up these three-dimensional constructs. So this is a cross-section you see here. Each of this is a single colloidal quantum well, and then we make this slabs of quantum structures. And this is in large scale what it looks like. So this is here for inch, which means it corresponds larger than 80 centimeters square. And this is almost my final slide here. You can really make active devices out of these colloidal quantum wells. This is in 2020, showing that we can actually achieve record high external quantum efficiency in the range of close to 20%. This is pretty much the theoretical limit. And this puts us on par with colloidal quantum dot materials, perovskites, so on. So we think, as also highlighted on the cover of Advanced Materials, this is really a new pathway for the entire community to make active devices out of these atomically flat materials. Just to conclude, colloidal nanocrystals, an important family of nanomaterials, enable high performance color conversion enrichment. This is now well acknowledged and indeed already found commercial use by us, but also many companies and communities around. One of the most important indeed development is one screen leader, Samsung, also our partner, where they're now really pushing LCD used in conjunction with these colloidal nanocrystals, and it's a disruptive effect because indeed, as a result, organic-based LEDs for TV use will further be pushed out, and LCDs indeed in the near future will continue to dominate. Colloidal quantum wells, a more recent family of the nanocrystals, offer record gain coefficients. This is the highest ever of all colloidal materials that we know. And indeed, we have two new directions, stacking them in ensemble. This gives us another degree of freedom, and doping them as we have been most recently doing. Before I stop, I'd like to also promote, if I may, our recent book that came out in Cambridge University Press with my co-author and close collaborator, Professor Sergei Gopanenko. In Applied Nanophotonics, you can find all these discussions in great detail if you'd like to know more. And this is a very self-contained book, so you can even do this as for fundraising. I'm very happy to acknowledge funding from Europe, in Turkey, and companies we are working, as well as those in Singapore. And finally, thank you so much for your kind interest and the time you had given me. Thank you.
Thank you very much, Mr. Demir. You have gave very innovative informations. We follow your work closely and you make us proud of your work. If you wish, I want to leave the question at the end and move on to the next speaker. Today, our another speaker, David Slovoda, continues his studies at Liberec Technical University. The Technical University of Liberec is a university in the city Liberec in Czech Republic. The university has undergone great transformation in over 60-year history. The university's field of study includes science, nanoparticles and nanofibers, high-end textile engineering research, smart fabrics, electrospinning, and protection with the help of the nanotechnology and exactly automotive industry. The university has adapted its research focus to meet the needs of local industries. As such, the university has strong ties to the local companies with the emphasis on the local environment and ecology. David Slovoda is a member of Academic Senate of Technical University of Liberec, and he co-founded initiative that helped to secure production of several million veils and respirators in 3 weeks. They helped the companies with testing their materials and informing people about great potential of the nanotechnologies. I now give the floor our next speaker, David Slovoda. Mr. Slovoda, your word.
Good morning. Thank you for your word. At first place, I would like to thank you for your invitation, and it's a great honor to be here with a person like Mr. Volkan Demir. It's amazing. I tried to read something about you yesterday, and I just couldn't understand how it works, but it must be amazing. It must be amazing. So
you're very kind. Thank you.
Thank you for invitation. I'm aware that in compare with you, I'm beginner, but I'm shortly, I will try to explain you the situation in Czech Republic during the crisis. So I will try to be pretty short. At the beginning, we were not prepared of this crisis. Nobody was. I'm talking about respirators and veils that are able to really protect you. They are able to catch virus or particles at the size of virus. I'm from a university that has, as Mr. Chairman said, long history of excellence in nanotechnology, and I decided to help with spreading ideas of professors who came up with solution. Thanks to my experience from European Parliament, I had some contacts on people from different fields. I co-founded non-profit initiation that connected academic world with business, with celebrities, with politicians. We started testing different materials and looking for suitable alternatives that that have high filtration effects, let's say. We promoted nanotechnologies as a great option for their great abilities to easily get on FFP3 level. Thanks to celebrities, people started to trust us, and we were testing different protection stuff, also from Asia. We found out that very often they're not on same level as they should be. Very often they are 3 or 4 times worse than they declare. And thanks to devices that invented Professor Lucas, that he will speak after me, we belong to top producers of veils and respirators with high quality in Europe. We help to secure huge production of protection stuff in less than 3 weeks. Since that time, I've been trying to help nanotechnologies in a way up. And my aim is to connect people that know what are they doing. So now we are in contact with aspirant for Nobel Prize, with Joe Biden's team, who will be the next president of USA, European deputies, to Czech companies. And my work is to interconnect these people to keep forward. So we are moving forward, and that's great. 2 days ago, I realized that in Czech Republic we have production of millions whales per week for 15 cents per one, which is great. So we are really moved to a higher level, and that I'm glad that nowadays we are independent and we are able to export this stuff. So that's all about my story. So I'm just a person who is trying to interconnect people that they know something to be better. So now I would like to ask Mr. Professor David Lucas, and he will explain you. He will explain you more about nanotechnologies.
Thank you very much, Mr. Slovoda. You provided very useful information. Now I would like to give some information about Professor David Lucas. David Lucas, Professor and Director Emeritus at the Technical University of Liberec, for years the head of the Department of Non-Woven Textiles within the Faculty of the Textile Engineering. He was a Fulbright Scholar in 2009 and 2010 with the Clemson University School of Materials Science and Engineering Lab Fluidics. Now today, David has succeeded in building a world-class lab with many of his PhD students becoming his colleagues. I now give the floor our next speaker, David Lucas. Professor, your word.
Thank you very much for introduction and also for asking me to be a member of this webinar. I would like to be sure that you see my presentation.
Yes.
Fine, now it works. I would like to speak about quite new method to produce nanofibers. This method is called AC electrospinning, and as you can see, that's a work of the Department of Bioengineering at Technical University of Liberec. Especially we are at the Faculty of Sciences and Humanities and also Education. Firstly, I would like to show you what is the difference between very well-known DC, it means direct current electrospinning, and our new method. Direct current electrospinning is visible on the left-hand side of this slide, and you can see that the liquid is transported from a so-called spinning electrode in fibers or nanofibers that are here depicted in red to the collector. And the main feature of this device is that you need two electrodes. Both of them are stationary charged, one of them positively and the last one negatively. On the right-hand side, you can see the method of so-called AC electrospinning. And in this case, surprisingly, it is not necessary to use the counter electrode, so-called collector. And in fact, it works like a shower of nanofibers. That's quite new method using which you are able to create nanofibers. I would like also to underline that before us, some authors also mention AC electrospinning, but because they were not using sufficiently efficient high voltage supply, they were not able to discover the effect that we are just now using for the AC production of nanofibers. Here is a scheme how, or information from Web of Science, how the interest of or about AC electrospinning is increasing by the numbers of publication per a year in this area. You can see the effect. What distinguishes AC electrospinning from DC electrospinning is that we are creating something what is called plume of nanofibers. And this plume of nanofibers should be manipulated, should be used for technologies that follow after the effect of nanofiber. You can see on this slide that we are trying to produce quite unusual nanofibrous materials like so-called composite nanofibrous yarns. In this case, we are able to wrap or to coil nanofibers around any linear textile product like monofiber product, multifiber product, or classic textile yarn. The scheme of this material is sketched on this figure provided by SEM, it means scanning electron microscope. You can see the velocity by which we are able to produce these yarns, and it seems to me that it is really on the industrial level. We are able, that's just the principle, we are also able to cover plates or planes by nanofibers. During the beginning of so-called Coro crisis in the Czech Republic, we were using this method to produce planar nanofibrous material that were used by university to produce special masks for our district. I would like also to underline that nanofibers produced by AC electrospinning are a little bit more exotic. compared with nanofibers produced by DC electrospinning. There are more torch. There are also something like varicose. It means they have different radii along the axis of the nanofibers. I would like also to show you how looks like the breathing of the polymeric solution from which the nanofibers are creating as the consequence of hydrodynamic instability, how jets that are after that transformed into nanofibers are creating, dying, and creating again with a very high repetition. So I would like also to show you that in fact AC electrospinning is dangerous that just for 3 centimeters above the spinning electrode, because after that the charges that are involved in nanofibers are in fact neutralized. And using this movie I will be able also to explain you the principle of AC electrospinning. We simply create, for instance, positively charged nanofibers that are moved to 3 centimeters above the, or emitted, they are emitted from the spinning electrode. And after that, they are serving as a counter electrode for next discharge that is created using opposite charge. So that is why plus and minus electric forces are enabling this effect that doesn't need so-called counter electrode. Here you can see the effect by which we are able to create these nanofibers in different, using different frequencies of the electric field. I would like also to underline that it seems us, and we have some very strong evidences that AC electrospinning for some polymers is more efficient. It means more productive for production of nanofibrous layers and materials. I would like also to show you that as opposed to DC electrospinning, we have in our hands the possibility to change the frequency of the waveform. And you can see that surprisingly the efficiency, it means the mass of the nanofibers that are creating by a special spinning electrode or particle spinning electrode per 10 minutes, how it deepens, and that we are really able to enhance the efficiency of these devices just with changing the frequency of the waveforms. Here are some snapshots or photographs from the Coro crisis, and I am proud of the fact that the team that supplies our district, it means the Liberec district, with nanofibers in the period of time where they were not available at the Czech Republic, was established, or members of this team were our students, professors, colleagues, or doctor of all, how to tell that, of all scientific orientations like mechanical engineer, physicist, chemists, students who are studying technology, and so on. Just now, I would like to show you our quite new idea how to utilize AC electrospinning that is able to create these composite nanofibrous yarns. And we are just now trying to braid by very specially designed braiding machine, so-called sutures for medical application. And we think, or we believe that the advantage of such sutures will be that nanofibrous material will enable a better interaction with living cells that should be attached to this suture. And also we are able to incorporate many biologically active chemical agents into the nanofibrous yarns that will be able to support the healing process. I would like also to underline that we are able to create these sutures from polymers that are fully biodegradable, and that is why these sutures should be applied as something what is not necessary to be removed from the body of patients. So thank you very much for your attention, and if there will be some questions, we are prepared to answer it. Thank you.
Thank you very much, Mr. Lucas. We are already considering the benefits of these developments. I would like to add some information. Our next speaker fields solar energy. In the adventure that started with a solar-powered water pump in the 17th century, a very good progress has been made today. The biggest reason for the interest in solar energy in the historical process was oil crisis experienced in the 1960s. After this crisis, a search for alternative energy source was started, and it resulted in people obtaining their needs from different sources. Solar energy for use in the invention and has gained importance in Turkey. The first National Congress of Solar Energy was to 1975. Since that period, studies, knowledge, and activities in this field have increased with the work of experts and universities. Kalyon Energy has made a great investment in the continuation of these researches. Mr. Fırat, the manager of the R&D center within the company, is one of our speakers today. Fırat S. completed his bachelor and master degrees at the physics department, and he completed PhD micro and nanotechnology of Middle East Technical University in Turkey. He worked as a researcher in Gunam Research Lab. Their main target solar cells. In 2019, he entered Kalyon PV as a cell model integration manager, and from 2020 till now, he working as R&D manager for Kalyon PV integrated factory. Now, I want to give the floor to the last speaker, Fırat S. Mr. S., your word.
Thank you, Berkan Bey, for your kind introduction. Let me share my screen for my presentation. I think you can see it right now. So today I'm going to talk about a specific application of nanotechnology on photovoltaics, because this is our expertise as a company and also for me. First, let me give a short introduction to our factory, who we are. We are in fact a module manufacturer, crystalline silicon photovoltaic module manufacturer that has a 500 megawatt production capacity per year, which is the biggest in Turkey and in the region of Europe and Mediterranean area out of China. And our main difference from the other module manufacturers is that we have a 75% localization ratio, which is thanks to the fully integrated production capability of our factory. When we say fully integrated production, what do we mean? I will explain shortly. The cells that consist of our modules are also fabricated in our factory, and also the wafers that we produce ourselves on top is also produced in our factory, and semiconductor ingots, crystals, are also fabricated in our factory by polysilicon material. So we start from the raw material and fabricate ingot, wafer, cell, and module at the same time. In addition, we have sorry?
Já mám nějaký videokol, jo, ale teď tam nic neříkám, ne, povídejte klidně.
Okay. And we have an R&D center of 100 researchers located at the same factory under the same roof. So we are producing our technology together with our products. Let me shortly give an introduction of the structure of a basic crystalline silicon solar cell to give you the idea in a better way. So we have a P-type mono or multicrystalline base, and we have an N-type diffused emitter for p-n junction formation on the front side. And on the surface, we have texturing for light trapping. Since we are using solar energy, we have to trap light in order to convert energy more efficiently. We have the anti-reflective coating, again, to remove the reflection from the surface. And we have the contacts in our solar cell. And principally, how a solar cell works is light comes into the solar cell, it generates electron hole pairs, and these electron hole pairs are separated by the p-n junction electric field, and they are connected by the silver grid and aluminum on the rear and front side. And today I'm going to focus on the surface of the solar cell, which enhance the light trapping of our solar cells. So when I say light trapping, what I mean, let me quickly show you. When you have a flat silicon solar cell, flat silicon surface, you have just light entering to your silicon wafer, and it travels a minimum distance inside your cell, and it escapes. However, when you have a textured surface, when you have some texture on the surface of your wafers, you can have this light traveling more distance inside your solar cell, so absorption probability is increased. Therefore, you get more efficiency from your solar cell, and you can see the surface of a industrial monocrystalline silicon solar cell, where you have micron-sized micropyramids on the surface that enhances this light trapping. And also for multicrystalline silicon solar cells, since you don't have a definite crystal structure, you cannot make pyramid surface texturing, but you can make isotextures, which are some random microstructures on the surface of a multicrystalline silicon solar cells that enhances light trapping. So this path and length enhancement by total internal reflection and decreased reflection by multiple bands effect increases the solar cell efficiency. And today we are going to focus on the multicrystalline silicon solar cells, because multicrystalline is a cheap material, and in terms of cost per watt, it is competitive to monocrystalline silicon, which is the product that we are producing in our factory right now. So the wafers that we are using in our factory and in the photovoltaic industry are cut from ingots using two methods. One you can see here is multicrystalline wafer with slurry cutting and diamond cutting. Slurry cutting means that you are using a cutting fluid, and it results in inhomogeneous surface crack distribution and kerf loss. You have a high kerf loss in this type of cutting, and you can see that you are having a rough surface and there is no reflection from the surface. However, when you use diamond wire cutting, it results in a rather smooth surface with a very shiny surface, and it has a low kerf loss, which means that when you have diamond wire cutting of your wafers to produce solar cells, you are having cheaper materials because of the less material loss from the kerf loss. So here, for multicrystalline texturing or isotexturing, we are using some acidic solutions which contains the oxidizes and etches silicon, and it is sensitive to starting surface, which means that if the starting surface is rough, as in the case of slurry cutting surface, you can make isotexturing on your multicrystalline wafers. However, if the starting surface is not so rough, it is smooth as in diamond cut wafers, you cannot make this isotexturing on the surface of your multicrystalline wafers. So diamond wire sewn multicrystalline wafers cannot be isotextured effectively, which is a problem of industry right now. And the solution of this is the nanotexturing, which is also applied industrially in crystalline silicon solar cells. So what are the alternatives for texturing of multicrystalline silicon solar cells? We have plasmonic scattering, laser texturing, plasma texturing, reactive ion etching, and photonic crystal scattering methods, which are low throughput and vacuum processes, and they cannot be applied all to large areas, so they are not industrially feasible. However, there is another solution which is called metalisted etching, which is a solution-based method, so it's easy to implement. It's applicable to large area and batch process, so you can have high throughput, and it's a top-down approach for nano processing, so control of electronic and mechanical properties are easy. And you can make range of structures like nanowires, nanoholes, nanocones, and microwires. And what is metallisted etching? Basically, it's using metal as a catalyst to etch silicon randomly using some oxidation of silicon under the silver catalysts so that silicon is oxidized faster under the metal and etched by hydrofluoric acid, and metal sinks. And by this method, it occurs recursively, and the reaction continues. And using this method, you can make nanowires in front of your solar cells. You can see nanowires on the surface of silicon here. You can make nanoholes, nano-sized holes on the surface, and nanocones on the surface of your solar cells. And before texturing, your multicrystalline wafer looks like this. It's pretty shiny, but when you make this nanotexturing, you get a completely black solar cell, which means that you are having very low reflection from the surface, so you can harvest the solar energy in the limits. And this is called black silicon concept. And this concept is applicable to industrial silicon solar cell production. In the standard production, we are using isotexturing, doping, junction isolation, passivation, antireflective coating, and metallization. However, in diamond cut multicrystalline cell process, you cannot use isotexturing directly, so you have to add one more method step, which is metallisted etching in front of your production line, and you can start your process with metallisted etching and continue production. So, which means that diamond cut multicrystalline cells can be textured with this metallisted etching nanotexturing method. And metallisted etching is here used as a preconditioning step, or it can be used as a final step to cover your surface with nanowires. And it creates edge pits on the surface to enable initiation of isotexture. And this method is a new method, but it's being developed. There are some articles showing that it's applicable to industrial silicon solar cells. And also there are some products, industrial products, that apply this process to industrial production lines, which is also one of our partners working on this project. And forecasts show that in the near future, multicrystalline, high-performance multicrystalline solar cells and cast monocrystalline solar cells are going to dominate the market. And we are seeing that the curve loss is forecast to be dropped in the coming years. And also we see that metal catalyzed chemical etching, it's a wet chemical nanotexturing method, is going to be dominating technology in 2030 for the whole world production market. So this brings me to the end of my presentation. Thank you for your attention.
Thank you very much, Mr. S. Very nice information that you provided. Now, with your permissions, I want to move on the question our viewers have asked. It looks like we have some questions. One question is for Professor Hilmi. Let me find. Professor Hilmi, thank you for the detail that you shared. I wonder that if your lab studies covers UVC range, especially 222 nanometer wavelength. On the other hand, if not, is it possible to focus on this range with your current resources?
Well, thank you very much. This is a wonderful question by Mr. Mustafa Basharan. Yes, we have been working on near UV and deep UV range. We do have research results towards deep UV using LEDs, but also other devices. However, for 222 nanometer range deep UV LEDs that we have been looking into have not been commercialized at the moment by us. We do have another range which is 260 to 280 range that is commercialized. We also collaborate with a company from Sweden where we have developed another technology based on on-chip integrated cathodoluminescent devices. These devices are actually cheaper and they are extremely efficient in terms of germicidal performance, and those are now commercially available. So this range is carefully chosen so that the disinfection efficiency is the highest. And with these devices, together with Sweden, we have demonstrated log 8 to log 6 performance in terms of disinfection. This includes coronavirus, as well as variety of viruses that our collaborators have chosen, and also some bacteria colonies. So deep UV is now extremely interesting, and we are quite active in this range. Thank you.
Thank you, Professor Demir. Thanks for your nice answer. There is another question to Mr. S. from Gentaş, Turkey, Haim Rosenblum. The question, procedure of decorative laminates and surface. First question to Dr. S. Any developments or future improvements regarding the dust and humidity accumulation on the PV panels? Dr. S.
Thank you, Mr. Haim. In fact, there are two approaches. One of them is, of course, cleaning of the surface of the modules, which is a hard task in the field, but we have to do right now, and we are still developing a robotic cleaning machine for our own solar power plant. However, in order to prevent this soiling and dusting on the surface of the modules, there are some applications like nano coatings on the surface of the glass, which we also worked in the past. But the main problem of these coatings on the surface is that with time they degrade very quickly, and they can be easily scratched, and after some time, due to the dirt and dust, they delaminate easily. So that they lose their functionality in time. So for the main target for the development of these nano coatings for anti-soiling and anti-dusting, maybe to increase their lifetime on the surface of the glass panels.
Thank you, Mr. S. Also, there is one short question, I think just one sentence you will answer. What is the efficiency of the solar cell that are produced? Yalçın Yılmazkaya.
Thank you, Yalçın Bey. Yesterday, from our production department, we got the latest results. Their medium average production efficiency is 22%, and they are going up to 22.2, 22.4% in the tolerance limits of the measurement, but the average is around 22% right now.
Thank you, Mr. S. I think there are not more questions now, but I just wonder about to Mr. Slovoda, if you are available to answer my question. If Turkish companies invest in Czechia, is it possible to collaborate with universities and industry? Is it easy?
Well, sorry, again, please.
If the Turkish companies invest in Czechia and open the company, and is it possible to collaborate with your university and industry? Is it easy to be different companies?
Yeah, well, that also can be a question for Professor Lucas, because he's very often managing the project. But yes, it's normal in practice. Well, yeah, it's usual for Czech companies, for foreign companies. So yeah, it's possible.
Thank you. And I think just asking for the Yiriku's, how successful is the Czech Republic in the sphere of nanotechnologies compared to the world? Thank you.
No, so as I said at the beginning or during my presentation, Czech Republic is quite strong in application of certain types of nanotechnology, and especially it is nanofiber. So we are well known in terms of nanofiber production machine, which is called NanoSpider. and you can find it everywhere in the world, in labs, but also in industrial companies. And regarding, so when you ask successful nanotechnology, nanotechnology is so broad that we have to focus to some part of it, and Czech Republic is very successful in nanofiber. Besides, we are also well known for electron microscopy, which is not exactly nanotechnology, but the tool to study nanotechnology. I don't know if you know that in Czech Republic we have 3 major electron microscope companies in Brno, and one of them is Czech company 100%, which is company Tescan. And one also very interesting type of nanotechnology is nanostructuring plastic. We have a very nice company in Prague which started to work internationally on that concept, which can be used for illumination, for instance. So they have a partner in Germany which is manufacturing lights using, instead of standard optics, this nanostructured flat plastic which works like optics. So yes, we are successful in certain type of nanotechnologies. For sure, we are still very small country, so we cannot compare with the USA or China or Japan. But nevertheless, we are very good at some times. And maybe regarding the type of cooperation on a business level with Turkish companies. So if you want, you can find a partner, set up a limited company to have you can have a share in Czech companies, you can invest. So I believe that Czech Republic is a very open country to foreign investment or business partner, or you can become also the distributor of Czech companies in Turkey or in Middle East or other parts of the world.
Thank you, Mr. Yerikus. There is another question. I think this question going to Mr. Lucas. Would it be possible to produce nanofiber from cellulose and lignin?
Just now I didn't understand. Nanofibers from what?
Yeah, cellulose and lignin.
Cellulose and
lignin.
Lignin. Yeah,
lignin.
yeah. Just now I understand. It is well known that cellulosic nanofibers exist, and there are a lot of articles that are describing the production of nanofibers from various kinds of cellulose. On the other hand, I have no information about the possibility to spin lignin. The reason for that is that the lignin molecule is not a linear one, but it is like a star molecule, or it has a lot of branches. And it is well known that branched carbon polymers are not well spinnable. That is why I suppose that the research and development in this area will need maybe next 2 or 3 years. There are a lot of companies, especially from the north of Europe, like in Sweden or in Norway, where in fact lignin is produced like a byproduct of industries manufacturing wood. And lignin is a very good candidate to be carbonalized to produce carbon nanofibers. So I agree with the person who is posed this question that lignin is something really very important for researchers to find some ways how to electrospoon it.
Thank you, Professor. Also, there is one additional question maybe you can answer. What is the nanofiber diameter range for some specific polymers with AC-type electrospinning? for example, for TVD, TPU, and PA6 from Volkan Demirel.
The question about the diameters of nanofibers is not a question, in my opinion, or from my experience, it is not the question about the engineering of the spinning device, but that's in fact included in the preparation of your polymeric solution for electrospinning. And we met several times with the fact that if you put inside the polymeric solution some additives that is in a really trace amount of lower than 1%, then you are able to influence heavily the spinning process, the diameter of fibers, the rate of evaporation of polymeric solution, and also a type of crystallinity. For instance, working with polyamide 6, spinning from carboxylic acids, if you add some anorganic acids, you are able to influence the percentage of so-called alpha or gamma phase of crystallinity. So my answer is that in fact, how to influence the diameters of fibers is more caused by polymeric solution and the recipe for it than the type of electrospinning, if it is AC or DC. And I would like to add maybe the last sentence, that it seems us that DC and AC electrospinning provides us with nearly the same diameters of fibers.
Thank you, Professor. And I think there is another question to Slovoda, I think will be answered maybe. Is there any R&D center in Czechia designed specifically for foraging companies, or foraging companies use the same R&D center under the universities? Mr. Yalın Yüreğil.
Well, so this is also, this is also a question about cooperation, right?
Yeah.
So as for me, in this case, it would be best to that I can give you my contact, my email address, and all companies can text me what they really need, and I can interconnect them to, for example, companies or politic, all politic field which they would like to go. So I can just help them with their way. So as for me, it would be the best to give them my email, and I can help them. I can interconnect them.
Thank you, Mr. Slovoda. And last question, I think we have already, our time's up, and I want to just one short question to Mr. S. Arif Hışır. I would like to ask about the dye-synthesized solar panel. As you know, Picoline macromolecule-based dyes are used in solar panels. So the Picoline dyes are synthesized by yourself. Could you please open your microphone? Unmute, please. Yeah. Okay.
Berkan Bey, I think this question is not coming to me because it's about dye-synthesized solar panels, which is not our technology. We are having crystalline silicon solar cells. So this question...
so maybe it is different kind of search, and kind of, maybe yes. Other... okay, thank you for everybody. Before the closing the meeting, I would like to thank Istanbul Czech Embassy Commercial Attaché Mr. Jan and Mrs. Neil from DEİK organization. Great, thank you everyone. We appreciate you being here. Thanks again for joining us today, and we will see you next time.
Thank you. Bye-bye.
Thank you.
Thank you. Goodbye.
Goodbye.
Bye-bye.